Hello. This podcast is the first in a two-part series on how to use kinematic graphs to represent and describe uniformly accelerated motion. We'll learn how to find velocity from position time graphs, how to find displacement from velocity time graphs, and how to find acceleration from velocity time graphs. In a previous unit, we learned how to do the first two topics for constant velocity motion. Now we're going to learn how to do them for uniformly accelerated motion. First, let's start with finding velocity from position time graph. Now, we took a look at this back in our constant velocity unit, and it's the same thing. The instantaneous velocity is equal to the slope of the position curve. Only in accelerated motion, this velocity is constantly changing. So we have some different techniques to find the velocity. First, we can use the slope of the tangent line, or we can take the average velocity for a time interval, making sure that our time of interest is in the middle of that time interval. Let's take a look at how we use these two methods. Here's a problem. Find the instantaneous velocity at 3 seconds. Well, that'll be the slope of this curve at 3 seconds. The first way we can do it is the tangent line method. So we draw the tangent line at 3 seconds. And then we go ahead and take our final position, initial position readings, as well as our final time and our initial time readings, and we calculate the slope of that tangent line. And we wind up with 11 meters per second. Now, this is a time-consuming way and not particularly accurate. A more accurate way is to use the average velocity method. So here we need to pick a time interval where 3 seconds is right in the middle. So we could have picked 1 to 5 seconds. I chose to pick 2 to 4 seconds. And then we just simply need to take our position and time readings at 2 and 4 seconds, and we use our formula for average velocity. Displacement is divided by elapsed time, and we wind up with 11.5 meters per second. So whenever possible, the average velocity method's preferred because it's quicker and more accurate. Let's talk about some general cases when we're finding velocity from position time graphs. We saw how to do it analytically. Now just look at some qualitative assessments we can make. We've got two graphs, both of accelerated motion. And if we look at the slopes on this first graph, we notice some symmetry right here at the middle. That's where it changes from going in the positive direction to the positions now moving back towards the origin and the object's moving in the negative direction. And we drew our tangent lines at just a couple different arbitrary points on each side. And we can see that we're going here, steeper slope. Now the slope's getting flatter, and there the slope is 0. If we call this section 1, we'll notice that this represents a motion that is slowing down in the positive direction. We know it's slowing down because the slopes of the tangent lines are getting flatter and the graph is moving in the positive direction. Now, if we take a look at section 2, we notice that the slope starts out at 0 and it's getting steeper and steeper. So on this side of the graph in region 2, the object is speeding up because the slopes are going from flatter to steeper, but we're going in the negative direction. Now let's take a look at the other graph here, and we can do the same markings on this, and we can split it into two regions about this point of symmetry. Here, our slopes are going from steeper to flatter in the negative direction, so that tells us that in this region, the object is slowing down in the negative direction. And over here in region 4, we go from a 0 slope to steeper. So anytime we go from flatter to steeper slopes, we are speeding up, and in this case, we're speeding up in the positive direction. This is how you can qualitatively assess the motion just by looking at the position time curve. Let's move on. How do we find displacement from velocity time graphs? Well, we learned in constant velocity that displacement equals the area between the velocity line and the time axis. Now, with constant velocity, we were dealing with flat lines for velocity, so we were looking at finding the area of squares and rectangles. Now, in accelerated motion, we are going to have straight lines that will have some sort of positive or negative slope. We're going to use the same process as before, and let's look at this example. Find the displacement for t equals 0 seconds to 3 seconds. Well, we go ahead and find the time interval and then outline the area between the time axis and the velocity line. Instead of getting a box or a rectangle, we get a triangle. Still, we need to find the area, and the area of the triangle is 1/2 times the base of the triangle times the height of the triangle. We go ahead and find the base is 3 seconds, and the height is 18 meters per second. We go ahead and do the math, and we have a displacement of 27 meters. Now, sometimes you'll get a trapezoid. Let's take a look at this example. Find delta x for time equals 4 seconds to 6 seconds. Well, now here's 4 seconds. The velocity, the initial velocity is not 0, so we're not going to get a triangle. And here's the other end. So if we just outline that, we can see that this forms a trapezoid. But we can break a trapezoid into a triangle and a rectangle. If you know the formula for the area of a trapezoid, you can just go ahead and use that. I find it easier to break the trapezoid into a triangle and a rectangle because I remember what those area formulas are. First, let's go ahead for the box area, or in this case the rectangle, and find the area. The width of this box is 2 seconds. The height of the box is 24 meters per second, and we're left with a displacement of 48 meters. But we're not done yet because we still have the triangle. The base of the triangle is also 2 seconds. The height of the triangle is 12 meters per second, from 24 to 36. Don't make the mistake of thinking this is the height of the triangle. It's not 36. Our triangle starts at 24 meters per second, so the height is only 12 meters per second. And that gives us a displacement of 12 meters, and we have to add these together, and we wind up with the displacement from 4 seconds to 6 seconds is 60 meters. Now, the same rules about being below the time axis apply here as they did with constant velocity. If you're finding areas below the time axis, if you're doing displacement, they are negative areas. If you're doing path length, all areas are positive. Let's take a look at finding acceleration from a velocity time graph. Acceleration is the slope of the velocity line, and let's talk a little bit about that. Acceleration is the rate at which velocity changes. That's the definition. Well, a slope always measures the rate at which our line changes. Specifically, it's the rate at which the y value changes relative to how fast the value on the x-axis changes. In this graph, the y-axis is velocity and the x-axis represents time, so the slope tells us the rate at which velocity changes as time changes. So that's why it's equal to acceleration. This is a straight line, so the slope anywhere on this line is going to be the same. When we deal with uniform acceleration, uniform means the acceleration is constant, so we would expect our velocity lines for uniform acceleration to be straight lines, and indeed they are. So we need to find the slope in order to calculate the acceleration. I picked 2 seconds and 4 seconds to do it, but you could have picked any other second. So the rise is 25 meters per second and the run is 2 seconds. Our calculation leaves us with 12.5 meters per second squared. When we have acceleration, it's not meters per second, but it's meters per second squared, because that represents how much the velocity, which is measured in meters per second, is changing every second. That's why you have the seconds squared in the denominator. As I mentioned before, velocity time graphs will be straight lines for uniform acceleration. Let's move on. Let's learn how to qualitatively, not numerically, but qualitatively determine the acceleration by looking at the shape of the graph. Here we have a velocity line that starts in the positive region at time equals 0 and it continues down into the negative region. I'm calling region 1 the positive region from here to here. If we take a look at this, we notice that the velocity is in the positive region, so this object is moving in the positive direction, but it's slowing down. So slowing down in the positive direction means that we have negative acceleration. The acceleration is in the negative direction. Because remember, when an object is slowing down, acceleration is in the opposite direction of motion. So since the motion is in the positive direction and it's slowing down, the acceleration has to be in the opposite direction. We could have determined that simply by looking at the slope, and we would know the slope of this line is negative, and since the slope of the velocity line is acceleration, our acceleration would be negative. Let's look at the second half of this line, which I'm calling region 2. The slope is still negative, so that's telling us that we're going to have negative acceleration, but let's look at how we would describe this. It's not slowing down because it's starting at 0 and increasing its velocity in the negative direction. So number 2, this region represents speeding up in the negative direction. And of course that's negative acceleration because anytime an object is speeding up, the acceleration is in the same direction as the motion. Let's look at another line. This line starts in the negative region and it moves up into the positive region as time goes on. The first half of this, the negative region portion of this line, I'm going to call region 3. If we look at this, the velocity is slowing down. So we start out at a relatively high velocity, and as we go on, we move towards the time axis. That means that we are reaching 0 at the time axis. So we are slowing down, moving in the negative direction. That means we have a positive acceleration. 2 ways we know that. Number 1, the slope of this line is positive, so that tells us we have a positive acceleration. Also, we know that when we're slowing down, the acceleration is in the opposite direction of the motion. So since the motion was negative, the acceleration is positive. Finally, let's look at the fourth region up here when this line is in the positive velocity range. We are starting at 0 here and getting to higher and higher velocities, so we are speeding up in the positive direction. Speeding up in the positive direction gives us positive acceleration, both because the slope of the line is positive and anytime you're speeding up, the acceleration and motion are in the same direction. Well, this wraps up part 1 of the podcast on how to use kinematic graphs to represent uniformly accelerated motion. I hope this helped, and have a good day.